So this series is going to talk about waves. So we're going to mainly be focusing on sound and light. These two are tightly linked because they both are different types of waves. So we're going to start off first talking about the basics about waves and then move into the specifics on sound and light. They do share some properties because they are both types of waves. So some of the stuff will be familiar from one when we get to the other. So waves, what are waves? They are wiggles in time and space. I know that sounds weird, but when we think of waves, we usually think of water waves. But as we're going to find out, sound and light are not going to be necessarily moving something like water. And so I found wiggles as a description somewhere, and I really like that because they are kind of doing the wiggly, jiggly type thing. And they're transporting energy, and that's an important thing. They are actually bringing energy with them, and how fast they're doing it, and the amplitude or how big their waves are determines how much energy they have. So we'll be looking at that for some of the different waves that we're going to look at. So we will be seeing these terms because they are described in terms of their frequency, their speed, their amplitude, and their wavelength. And this is for all kinds of waves. We use these terms. So we'll talk about these terms in a little more detail going forward. You do need an energy source in order to create the vibration. So you need some sort of source to start that vibration. So if you think about like a wave in water, it can be started by, for example, a person in the pool or dropping a pebble in the water. And it does need a medium for most of the waves, except for light. We'll talk about light when we get to that section. So medium meaning it needs air, water, a solid. It needs some sort of particles in order to transfer the energy. Like I said, light is the exception, but all of the other waves that we're going to be talking about require some sort of material in order to move that energy as the wave. The medium itself doesn't change, it just transfers the energy. So think about, again, like a pond. When you drop a pebble in, the water is still there after the wave goes through. So the medium, the water, the air, the solid doesn't change. It just allows that energy transfer. So let's talk about some of these terms that we describe waves by. So first, let's just look at the wave itself. So when we talk about waves, we'll see that the waves aren't all the same kind, but we generally turn them into a wave that looks like this because it's easier for us to be able to interpret and measure. And so when we draw the waves in this manner, we use these same terms. So we've got crest. So crest, just like a crest of a hill or crest of a mountain. So the crest is the highest point on a waveform like this. And then trough is the lowest point, just like the trough of a wave out on the ocean. So the trough is the lowest point on a wave. Amplitude, you can see marked here. So the amplitude is the distance of that wave from the midline. So you can see that we've drawn a midline on this waveform, and that splits the wave exactly in half. And the amplitude is the distance from that midline to the highest point of the crest. Or we could also draw the amplitude from the midline to the lowest point of the trough. So you can go either way and measure the amplitude. And amplitude, there you go, distance from equilibrium to the largest displacement. Wavelength, see the wavelength is marked here. So what does that mean? So you can actually mark the wavelength in multiple ways. So it's marked the wavelength from crest to crest. You can also mark the wavelength from trough to trough. What you're looking for is to include the entire wave. So we could also mark the wavelength from any point on the wave to its equal point. So we can mark it from here to here, and that includes the entire wave because we marked from the starting point before the crest to the starting point before the next crest, and that gets us the full wave. We want to include the entire wave in our wavelength. You'll see that the wavelength is represented by our little symbol here. So if you ever see this little guy, that is representing the wavelength, the amount or the distance between, like I said, the crests or the troughs. That's the most common place that we mark it. But like I said, we can mark it from any identical point on the wave as long as you include the entire wave. All right. So it is the distance between those adjacent crests or troughs. The next one is frequency. So frequency is going to talk about the number of cycles per second. So a cycle is just a full wavelength. So you can see that here. So the cycle is right here. So that's one cycle. So then we've got another one here. So, oop, grabbed me. So we've got a second cycle here and then a third cycle here. And so this, it's got marked up here as 3 hertz. That is talking about the frequency. So it's got 3 cycles per second. So this is 1 second, 3 cycles, 3 hertz. So there we go. So it is measured in hertz, HZ, and it's just the number of, like I said, the number of cycles per second. So if you've got 10 cycles in 1 second, it's 10 hertz. So, you know, we talked in the electricity chapter that our electricity, our AC, is in 60 hertz. So that means that the electricity alternates 60 times a second. So it's related in a way to our waves here. So let's talk a little bit more about frequency. So like I said, the unit is in hertz. It was named after Heinrich Hertz because he was the one that first demonstrated radio waves in 1886. So he got the unit named after him. So 1 vibration or 1 cycle per second. So to give you an idea of the range of frequencies that we've got as far as radio waves, so AM radio is measured in kilohertz, K for kilo. So 960 kilohertz is the 960,000 hertz. If you listen to AM radio, you may notice that the stations are all in those 100 numbers. So the one AM station that I know around Columbus is 610, which means it would be 610,000 hertz. Now, if you think about FM radio stations have decimal points. So 97.1, 102.9, those are the ones I can think of off the top of my head. And this is because they are in larger units. So FM radio is in megahertz. And so they get the decimal point designation because you're going to add 3 more zeros. So they are going to be actually cycling faster. This is actually why you can get AM radio stations longer when you get farther away from them, like if you're traveling, than you can FM radio stations. The frequencies, the shorter the frequencies are, the faster that they use up their energy. So these guys, the longer waves, are able to travel farther and get their energy to your radio. There's one more, and that's your cell phones. These guys are in the gigahertz, so billions of hertz, and that keeps them from being able to interfere with other types of communications. But this is also why you have to have the stations around in order to get good signals. So that's why we have to have so many cell towers and satellite stations in order to get them to work. All right, so we now have these characteristics, things like wavelength and amplitude and so forth. The thing is that we can calculate speed for objects like cars, right? We know that you can do that by doing things like taking the distance, dividing it by time, and that tells you how fast they are, what the velocity or speed is. Well, we can do the same thing for sound. And so what we're going to do is we're going to look at these different characteristics, and we're going to take some of those characteristics and use them to calculate the speed. So you can get one wavelength per one period, or this formula T. Now, we didn't talk about periods, but this is basically the time for the wave to repeat itself. So this is basically a cycle, okay? But we often don't have the period. What we usually have is the frequency. So what we can do to calculate sound is find that the speed of sound for any time that we're looking at it is the wavelength, so the space from crest to crest, times the frequency will give us the speed of sound. So if we, for example, know that the wavelength is 10 meters and it is 60 hertz, I just made these numbers up, so they're not actually real numbers. But if this is the data that we gather, 60 hertz times 10 meters, then that would mean that it's moving at 600 meters per second. Okay? Okay, and we can also do this not just for sound, but we can also do this for light, because light is the same sort of wave. We can measure the wavelength, we can measure the frequency, and we can calculate the speed for it as well. All right, so let's talk about types of waves, because there's more than one type of wave. So we have transverse waves. Here, the vibration direction is perpendicular to wave propagation. So what do we mean? So here, the direction of wave motion is up and down, and the wave motion is forward and back. So that's what we mean by perpendicular. So the waves are going up and down while the actual motion is going back and forth. So think about like a plucked string or a jump rope, right? If you flick a jump rope up and down, or like a wave on water. So those all are doing the same sort of thing. The wave is going up and down while it moves forward. Transverse waves, these guys can travel through solids, liquids, and a vacuum. So they can travel through material, well, they can travel through areas where there is no material. So like the vacuum of space. But they can also travel through solids and liquids, but they are not able to travel through gases, just due to their nature. So surface waves, like water waves, are transverse waves. And then electromagnetic waves, like light waves, they're not the only ones, but light waves are the ones that are going to travel as transverse waves. The other type of wave that we've got is what we call a longitudinal wave. And longitudinal waves are going to travel a little differently. So instead of traveling up and down, they're going to travel by squishing and spreading. So the vibration direction is parallel to the wave propagation. So you can see here that the direction of disturbance is in the same direction as the wave motion. So I'm going to post a video actually of these two different wave types with my assistant and a slinky so you can see how this works. So here, like I said, the particles in the medium move closer together and farther apart. So they're going to get squished and spread, squished and spread. Longitudinal waves can travel in solids, liquids, and gases. So they can travel in all of the different phases that we've talked about before. And the best example of a longitudinal wave is sound waves. So sound waves can travel in all of these mediums. And the one thing that longitudinal waves cannot travel in is a vacuum. So you cannot have a longitudinal wave move in a vacuum because it needs particles to squish and spread in order to move. All right, so that's the end of the introduction into waves. So the other lectures will cover specifics on sound and light.